All right. So remember, you have an assignment due today. You can hand it in after class, or you can hand it to my assignment box before 5 p.m. today. Okay, that was right. So today we're going to talk about game theory. It's a particular way of formulating economic theories. And why is it called game theory? A game is a situation where players, the participants, make strategic decisions. So in game theory, we're not really talking about games, like as in playing. Rather, it's a way in which we formulate any scenarios that involve decision making. We are going to describe a situation where the individuals involved need to make decisions in terminologies that somewhat resemble a chess game. The objective in game theory is to determine the optimal strategy for each player. Typically, in a class like this, you will have two players, and you have to figure out what they would like to do in each player. So what constitutes a game? Once again, imagine you're playing a chess game. What are the elements of a chess game? Let's say we're playing something like chess, right? Chess. When we play chess, you don't play it. Well, there are some people playing it, right? Typically, two players, unless maybe you're playing against a computer. Still, there are two players in the game. So the game has four components. One is there must be someone playing the game. So you have players. You have two players playing a chess game. You can have more players in some other games. Like Monopoly, you might have 6 players. So you have players playing a game. Now they play a game. When the players play a game, there are things that they can do. For example, the knight can only walk in sideways, right? Pawns can only move forward initially, and the queen can move pretty much any way she wants. So there are rules in what the players can do or not. So those are called actions, what they can do. You play a game for a reason. You play for an objective. In chess game, the objective is to remove the king, right? Basically, you win by going checkmate. So there are rules. In Monopoly, you win by forcing all other players out of the game. So that's the objective. The objective is defined with payoffs. Higher payoff means better. While in chess game, the player usually win by being the last man standing. Imagine in a game like poker, right? In poker, you very often keep track of the number of points you have. So that would be a payoff. Finally, given the players you are playing with, the actions you can take, and the payoff you're facing, you make a decision. What to do? That's the strategy. Each player formulates their own strategy, so you have strategies in the game, and our objective is to solve for the strategies. For example, in the public good example that we talked about, you have David, John, and Paul as the players. The actions they can do is to participate in funding the public good or not, and the payoffs are the benefits from having or not having the public good. Based on the benefit they can get from having or not having the public good, and based on their understanding on what the other players are, the strategies they formulate, we talked about last time, is that do not participate if the good can be funded by the other two players or no. So that's a strategy. participate if my contribution is needed, and not if my contribution is not needed. So that's formulating an economic scenario in the terminology of equilibria. And we're going to do that for the next 2 classes. We're trying to figure out what's the strategy players are going to take. That's called the optimal strategy, the ones that they're going to take. The way that we think about the strategy might not be completely intuitive at the beginning. So a strategy is optimal if the player has no incentive to deviate from that strategy. In other words, there is nothing better that she would choose. There's nothing better that she would choose. So when the public good can be funded by the other 2 players, well, you don't want to participate because that doesn't actually make you better off. But if the public good cannot be funded by the 2 other players, your participation is actually the better, because that would allow the public good to be provided. So what is an action that is optimal to take in one scenario might not be optimal to take in another scenario. If you participate, maybe I don't need to participate. But if you don't participate, I need to participate. Something like that. So what's the optimal action depends on the scenario. And we are looking for the equilibrium as defined by the pure strategy Nash equilibrium. The pure strategy Nash equilibrium says that each player has a single action, and given what actions the other players have chosen, each player has no incentive to deviate from her own action. So what this says is, you choose what you do, I choose what I do. Given what you do, I do not want to change what I do. And given what I do, you do not want to change what you do. That's a Nash equilibrium. So you do what you do, I do what you do. None of us want to change our mind. Nash equilibrium is all about stability, right? You do not want to change, I do not want to change. That's Nash equilibrium. It does not say anything about efficiency and whether generally it's actually best for each player to stay in the Nash equilibrium. As we'll see in a moment, actually, under the Nash equilibrium, no individual player can improve her own payoff by acting alone, right? So because that's the point of stability. Given what I do, you don't want to change what you do. That must mean that there's nothing you can do that can make yourself better off, right? And given what you do, I don't want to change what I do. That means that there's nothing that I can do that make myself better off. That doesn't mean that there's nothing I can do that make you better off, or there's nothing that you can do to make me better off. In particular, under Nash equilibrium, there are often things that if we can act together, that make us both better off. Nash equilibrium says that you can't make yourself better off by moving alone. Doesn't say that we can make all of us better off by moving together. Okay. So remember the difference. The very first example, you would see that. How do you present a game? A game is usually presented in a table like this one, where you have one player on the left-hand side and another player on the top. So next to each player are the actions the player can take. For example, in this case, player 1 has action 1 and 2, and player 2 has actions C and D. So the numbers, the numbers within each cell represent the payoffs in each scenario. For example, 10-10 is what happens when player 1 takes action 1 and player 2 takes action C. And 16-9 is what happens when player 1 takes action 1 and player 2 takes action D. Okay. The numbers are read in the following way. Where? Give up. Broke.
All right, but this doesn't actually allow me to go. Okay, here we go.
The payoffs are read in the following way. The number before the comma is the payoff of the player on the left, and the number after the comma is the payoff of the player at the top. So, for example, if player 1 chooses action 1 and player 2 chooses action D, then player 1 gets 16 and player 2 gets 9. So the players would go through the different actions possible and consider what's the best they can do, given what they know about the other player.
Now we're going to
solve this. So how do you actually solve for the Nash equilibrium? So Nash equilibrium is named after John Nash. John Nash is the character portrayed in the movie A Beautiful Mind. The guy who, like in the movie, like kind of gone crazy, right? Yes, like hallucination. So that's a movie about him. How do we solve for the Nash equilibrium? The Nash equilibrium we solve by drawing circles. I will go through the logic while drawing the circle so you can understand what the circle represents. Let's start with player 1. Okay. Now, player 1 has to choose an action given what player 2 has chosen. At this moment, we don't know what player 2 is going to choose yet, so we have to go through all possibilities. So suppose player 2 has chosen action C. We don't know that's going to be the case. We're just assuming that's the case. We're going to go through every single case. So let's assume that player 2 is going to choose action C. If player 2 chooses action C, and if player 1 chooses action A, we will be in the top left cell, right? At player 1 chooses action 1, player 2 chooses action C. We're going to be in the top left cell. Player 1 is going to get 10 in payoff. If player 2 chooses action C, but player 1 chooses action 2, we will be in the bottom left cell. Player 1 is getting 9. Now, since 10 is bigger than 9, it's better for player 1 to choose action 1 in this case. We're going to denote that by circling the payoff he's going to get in that case. Right? So if player 2 chooses action C, player 1 is going to choose action 1 because that gives him a higher payoff. Next, we're going to move on to action D. Suppose player 2 chooses action D. We don't know that's the case, but we have to go through every single case precisely because we don't know which case is going to happen. So suppose player 2 chooses action D. Player 1 choosing action 1 would give him 16, and player 1 choosing action 2 would give him 12. Since 16 is larger than 12, he's going to choose action 1. Once again, we're going to put a circle around the number representing his payoff in this case. Now that we have gone through all the possible actions by player 2, we're now going to consider what player 2 wants to go. Right? We have gone through the actions of player 2 and determined what player 1 wants to do. Now we're going to go through the actions of player 1 and determine what player 2 wants to do. Suppose
player 1 is going to choose action 1. Once again, we do not know yet. Well, actually, right now we do know player 1 is going to choose action 1. But player 2 might not know that. So player 2, suppose player 1 chooses action 1. What would player 2 do? Player 2 can choose between action C and action D. Action C would give her 10 in payoff. Action D would give her 9 in payoff. Since 10 is bigger than 9, she is going to choose action C. Now, let's circle that. Finally, if player 1 chooses action 2, what would player 2 do? Player 2 can choose between action C and D. Action C gives her a payoff of 9. Action D gives her a payoff of 12. Since 12 is better than 9, she's going to choose action D. Now, what you have here is that player 1 always chooses action 1, while player 2 might choose C or D depending on what player 1 does. Nash equilibrium is this Nash equilibrium would be represented by the cell with circles all around its numbers. In this case, there's only 1. Here. Nash equilibrium is the cell represented. Nash equilibrium is the cell with circles all around its numbers. You represent the Nash equilibrium in words by the actions taken by the players. Action 1, action C is the only pure strategy Nash equilibrium in this case. Let's consider why it's stable. It's stable because let's think about what happens if action 1 switches to action 2. If player 1 switches to action 2, it's going to get 9 instead of 10, so that's a reduction of 1. That's not a good idea, so it's not going to change. What if player 2 switch? If player 2 switch from C to D, she's going to get 9 instead of 10. That's also minus 1. So she's not going to be better off if she changes, so she doesn't want to change. So in this situation, neither player can make themselves better off by switching to another action. Okay, so that's why it's stable. No one can make themselves better off by switching unilaterally. However, Nash equilibrium is not necessarily efficient. Take a look at the bottom right corner. This one. Notice that in the bottom right corner, both players would be better off than in the Nash equilibrium. 12-12 instead of 10-10. So this is actually better. It's better, but it's not a Nash equilibrium. So let's take a look why it's not a Nash equilibrium. So 12-12 is better for both players. Let's say we are actually here. What would happen? Now, for player 1, he thinks about whether he can get high payoff by deviating from this better outcome. If he switches from action 2 to action 1, he's going to get 16 instead of 12. That makes him better off. So he's going to switch. He's going to switch. Once he switched, what would player 2 do? Player 2 would look at the situation and say, well, if player 1 is going to switch, then I would be better off switching from D to C because I get 10 instead of 9. So player 2 is going to switch also. And you get back to the stable outcome when neither of them wants to change, right? So efficient outcome is not necessarily stable. This is one of the ideas that is important in game theory. Efficiency and stability are two different things. The players do not necessarily actually need to go through this process in reality. We assume that they are smart enough to figure out that this would be the case in their mind. So given that they know the payoffs they're going to get, they would be able to figure out in their mind that only action 1, action C is stable. And that's what they're going to choose. That's part of the concept in game theory that we're going to come back to in a moment. We are smart, so the idea that we are smart enough to figure out what will happen in other cases, and we are smart enough to know that they're not stable, so we're going to choose a stable outcome. In this case, as I have already indicated, player 1 always choose the same action because it's better. This is called a dominant strategy. Okay? You choosing action 1 is called a dominant strategy or dominating strategy. So it's an action that is optimal no matter what an opponent does. Right? So it's always better. It's always better. Action 2 is called dominated strategy because using it is never a good idea. Right? Using it is never a good idea. So if a player always choose a single action, we call that a dominant strategy. And the one that he never chooses, a dominated strategy. In more complicated games, you might have no dominant strategy or no dominant strategies. There are cases where you might have no dominant strategy but dominated strategies. So in more complicated games, there are more possibilities. In this case, it's very simple. There's one dominant strategy and one dominated. Furthermore, action 1 is strictly dominant strategy because it's strictly better. 10 is strictly bigger than 9, and 16 is strictly bigger than 12. That's not always the case, because you could have a situation where one action gives you this. In one scenario, the two actions give you the same payoff, but in another scenario, one of the two actions is actually better. This is called weakly dominant strategy. And if you think about it, the case for the strictly dominant strategy is obviously very strong, right? It's always strictly better, then there's no reason why you shouldn't take it. The case of the weakly dominant strategy is slightly less certain. There's the same in one scenario and different in the other. But you can still argue that it's better to take action 1 in this case, right? You can never be worse off taking action 1. At worst, you are as good as choosing action 2. And sometimes it's better to choose action 2. Why not just choose action 2? So if you can accept that logic, then we can apply it in a moment. The idea is 2 actions, they're sometimes equal, but sometimes they're different. Why not choose the one that is sometimes better? So if you accept that concept, we can actually remove the actions that are not used in the game. In this particular case, player 1 never chooses action 2. It is as if action 2 never exists in the game. It's never used. it's like me asking you, like, if you have the choice of coming to CUHK or going to some like Zhuhai or something, or OU, right? I think anyone would choose CUHK over you, right? So that would not, an action that is never taken in any scenario would not be contributing to the game. So we can eliminate them. In this case, we can eliminate action 1. So we're going to eliminate it. It's never used anyway. So let's just remove it. But if you remove it, notice that now player 2 has no incentive to use action D, right? Previously, player 2 might choose action D because that gives her higher payoff when player 1 chooses action 2. But now that possibility is gone. That possibility is gone. She's now only facing choosing action C and get 10 versus choosing action D and get 9. So now using action D becomes a dominated strategy under this new scenario where we have eliminated action 2. So this time around, action D becomes a dominated strategy, and we can eliminate it from the game. In a large game, you might be able to do this for quite a few steps. You could be eliminating multiple actions from the game repeatedly through this process. So this process, in which the elimination of an unused strategy, right? The elimination of one dominating strategy. For player 1, he never uses action 2. So let's eliminate that. If the elimination of one strategy can lead to the elimination of another, because player 2 have no incentive to use action D anymore. This scenario is gone. Never happens. So understanding that, she's not going to choose action D. Notice that what we have left is the Nash equilibrium here. This process is called the iterated elimination of dominated strategies. And it's an alternative to drawing circles. It does not guarantee to give you the Nash equilibrium, because there are games where there are no dominant strategies. But it helps you simplify the game. Okay, so very quickly, let me do it again. Suppose Mary has chosen the action movie. David is choosing. If David goes to action movie, he gets 2. If he goes to romance movie, he gets 0. So he's going to choose action movie. If Mary has chosen the romance movie, David going alone would get 0. To the action movie alone would get 0. David choosing romance movie would give him 1. So she's going to choose the romance movie. If David has chosen the action movie, Mary going to the action movie with David would get 1. And going to romance movie would get 0. So she's going to choose the action movie going with David. And finally, if David has chosen the romance movie, Mary going to the action movie alone is 0. Going to the romance movie is 2, so she's going to choose the romance movie. And as you see, there are 2 cells with circles around its numbers. So there are actually 2 pure strategy Nash equilibrium in this case. They are action, and romance romance. Action, action, and romance, romance. The idea is they want to go to a movie together, right? So either they go to the action movie together or they go to the romance movie together. Is there any dominant strategy and any dominating strategy? Is there a movie that a player would never choose? If you look at this case, David would go to the action movie if Mary goes to the action movie. David would go to the romance movie if Mary goes to the romance movie, and vice versa. So there's no dominant strategy and no dominated strategy. This example is one that is less clear what it means in reality. So what it says is that if Mary goes to action movie, David would go to action movie. If Mary would go to romance movie, David would go to romance movie, and vice versa. There are two possible outcomes. They both go to the action movies, or they both go to the romance movie. How would they actually figure out what to do? Game theory does not tell you that. Doesn't. It doesn't have, because both outcomes are stable. So it says nothing about which case might happen more likely. As long as they're making decisions simultaneously, you can't tell which one is more likely. Even worse, if they're truly making the decision simultaneously, it seems that realistically, there would be a pretty high chance that they would make the wrong decision, right? If they're really making the same decision, they're making decisions simultaneously, right? There are two stable outcomes. So you choose one of the stable. You choose to go to the action movie. The other person chooses to go to the romance movie. It seems unlikely. There's no reason to believe that you would be able to actually arrive at the same action without some sort of communication. So all this says is, if they just happen to fall into that situation, right? If they just happen to fall into that situation, would they want to switch? Imagine like they have one way we can imagine is, let's say the two of them have free tickets, right? Let's say somehow they got 2 free action movie tickets. If they want, they can switch them to romance movie tickets. Would any one of them do that alone? The answer is no. That's how you can interpret it. Somehow they get 2 tickets for a movie. Does any one of them want to switch to another movie alone? No. But if they don't have tickets to begin with, what tickets are going to be? One way to avoid this indeterminacy is to have one player move first, right? The reason why we don't know what's going to happen is that it's partly because the players has to choose simultaneously, so it's hard to see what's going to happen in that case. But let's say one player gets to choose first. So what would happen? And let's say Mary moved first, right? Mary moved first. Should Mary choose between the 2 stable outcomes evenly, randomly? What should she do? The 2 stable outcomes, as we have already indicated. One case, action movie, gives Mary a payoff of 1. The other, romance movie, gives Mary a payoff of 2. It would be dumb to choose evenly or randomly, right? She should choose, if she gets to pick first, she should pick the romance movie that she likes more. She should pick the movie that gives her a higher payoff, instead of just choosing a movie at random. And that's okay, because after Mary has made her choice, David would follow. After all, we have already determined that it's better for David to go with Mary than going to the action movie alone.
So we know this is a stable outcome. This logic is more clear if I present it in a tree diagram. So I've copied the payoff from above. So in this tree diagram, you can see that if Mary moved first, she's on the top. So she's put up. So the player who's moving first is on the top, followed by David. Notice there are two Davids. There are two Davids here. In some sense, this is like quantum mechanics. The David in the world in which Mary has chosen the action movie is not the same David as in the world where Mary has chosen the romance movie. So there are two Davids. With this diagram, it's very clear what would happen when Mary chooses each action. Let's say Mary chooses the action movie. If Mary chooses the action movie, now David gets his turn. David will be choosing between going to action movie and going to romance movie and ruin the night. So he's going to choose the action movie. On the other hand, if Mary has chosen the romance movie, David can unwillingly go to the romance movie or go to the action movie alone, and that ruins the night. So he's going to go to the action romance movie. For Mary, she is now choosing between getting a payoff of 1 if she chooses the action movie, and getting a payoff of 2 if she chooses the romance movie. So since it's better, 2 is better than 1, she is going to choose the romance movie. So that's what she's going to choose. So this is called an extensive form game. This way of presenting the game is called an extensive form game. And we're going to see more examples of that in a moment. But the logic is you put the Let's be more careful about how I actually solve this game. Extensive form game has to be solved from the back or the bottom of the game. We first figure out what David would do for every possible actions of Mary. Why? Well, because we have assumed people are very smart. They are so smart that they can predict what the other players are going to do. For us, in solving the game, the ability to predict what others can do is the same as saying, please first solve what other players have to do, is going to do. So in terms of solving the game, the ability to make prediction into the future is the same as saying you have to solve the game from the back. David's strategy depends on Mary's action. So there are multiple Davids, as I mentioned. And we first solve the bottom layer. There's one game you have to solve where Mary has chosen action movie. There's another game that you have to solve where Mary has chosen the romance movie. So you have to solve these two games first. Mary then chooses the best outcome for herself from all the possibilities we have solved, taking into consideration David's response. So Mary's choice in this case is a last step. Once we figure out what David would do, that's Mary's prediction. Based on her prediction, she's going to make a choice. This way of thinking is called backward induction. And the game could be a lot longer than this in some cases. You will see that in assignment 4. There are some longer games. Tonight? Or tomorrow? When do you want it? When do you want it? Huh? Well, I'm going to post it.
So, backward induction, right? Backward induction. Start solving the game from the back. No matter how long the game is, that's what you do. Start solving the game from the back. So, let's go through that. Let's start with number one. So, number one is the same logic that we have shown. Number one, David is choosing between action and romance. 2 versus 1, action is better. In the second case, David is choosing between 0 versus 1, romance is better. And finally, Mary is choosing between 1 from action and action, and 2 from romance and romance. So she's going to choose the romance movie. So that's the logic of backward induction. Start from the back. Now the equilibrium concept. Why should Mary choose it? Why should Mary choose action? Choose the romance movie? We have intuitively argued why, right? That gives her the highest payoff. How do you actually rigorously write down the equilibrium? The equilibrium concept in extensive form game where players move in turns is called subgame perfect equilibrium. It's called subgame perfect equilibrium for the following reasons. First, subgame refers to each individual tree knot that we have already mentioned. This is a subgame. This is also a subgame. And this is a subgame, right? Subgame is just subgame is a game within a game. Each tree knot is a game by itself. Each tree knot has a player, actions, payoffs, and strategy. So each tree knot satisfies the requirement of being a game. Players, actions, payoffs, strategy. You have a strategy here, David is going to choose action. You have a strategy here, David is going to choose romance. So it satisfies the definition of a game. So a large game might contain many small games inside. Perfect. Subgame perfect. So the perfect refers to the strategy. The strategy each player chooses within a subgame has to be optimal in the game. That, in other words, David is always going to choose what's best, given what has already happened. In this case, David is going to choose the action movie. In this case, David is going to choose the romance movie. Right. What subgame perfect equilibrium does not allow is David doing something weird that is not in his benefit. Remember that in the end, Mary is going to choose the romance movie, right? So the case on the left never actually occurs in reality. If it never occurs, David could plan to do something weird. And it doesn't hurt him. The plan doesn't hurt him because the plan is never realized, right? We know the flow of time is going to go through, it's going to be romance and romance. This is the reality. This is the reality. The situation where they go to action movie never happens. So if David plans to do something weird here, it doesn't actually hurt him. The plan doesn't hurt him because the plan is never materialized. Subgame perfect equilibrium does not allow you to make such weird plans. You're not allowed to plan to do something suboptimal, even if the plan never occurs.
never actually carried out in reality. What does that mean? What that means is you are not allowed, the players are not allowed to make empty threats. Right? You're not allowed to make empty threats. For example, what would not be allowed is in an argument. The girlfriend threatens the boyfriend that I'm going to jump if you don't buy me the diamond ring. And then if the boyfriend doesn't really buy the diamond ring, she doesn't jump. Now that is completely normal, like this is completely normal empty threats, right? Like, if we broke up, I'm going to jump. Then you don't jump. That's not allowed. That happens in real world, but it's not allowed in subgame perfect equilibrium. Right? So it excludes. So the subgame perfect equilibrium excludes some interesting phenomena. So it excludes some interesting phenomena because empty threats do occur in real world. Right? But it's not allowed. It's not allowed. Why is it not allowed? Why is it not allowed? There is a reason why it's not allowed. Let's imagine what happens if we do allowed David to make suboptimal plans. Let's say this is David's strategy. This is David's strategy. He's going to choose action movie always. That's suboptimal in the right-hand case, right? In the right-hand case, if Mary has really chosen the romance movie, it is not in David's benefit to choose the action movie. But let's say this is the plan. What would Mary choose in turn? If Mary believes in David's plan, what would Mary choose? She's now choosing between going to the action movie and getting one, or going to the romance movie and getting nothing because they're going to different movies. Mary would choose action movie in this case. Suboptimal plans can alter the state of reality. This feels very much like Doctor Strange or something. Like there's something that happens in the future could alter what happens now. Right? So it's very much science fiction. The thing is, empty threats, if you allow empty threats, it can change what happens right now. Right? If you say you're going to jump and I believe you, then I'm much more likely to heal to what you want. Right? But if I think you're not going to jump, then I'll just do what I want to do. Right? So in subgame perfect equilibrium, we rule out the possibility that the players can make suboptimal plans like that. Those plans could alter what happened in equilibrium, and we do not allow that. Every player has to make a choice in every scenario that is optimal within that scenario. So it's a restrictive definition, but it helps us to keep the situation manageable, right? Everyone has to make a decision that is optimal within that plan, within that particular scenario. So, So the suboptimal plan alters equilibrium. So if you write a strategy, so the strategy that they're going to choose is David's strategy. David would choose
the optimal strategy is David is going to choose action if Mary chooses action, and romance if Mary chooses romance. And Mary's strategy is simply romance, right? Mary, who chooses first, always pick romance. David followed by picking romance. So romance is equilibrium, but action is not. In the extensive form game, in subgame perfect equilibrium, only romance is the equilibrium. When they move together in the normal form game, action is also equilibrium. So we actually have gone from two equilibria into one equilibrium. In some sense, you can say Mary is picking the equilibrium that is best for her. So that's the first mover advantage. When you have more than one Nash equilibrium, the player who moves first can get to pick which one. When there's more than one, she gets to pick which one. So there's some benefit in moving first in these games. Now, before we go to the next exercise, let's think about whether this is realistic. So extensive form game made at least 3 contestable assumptions. One is the ability to make predictions. Hyper-rationality. Players are capable of doing backward induction for very long games. So the players are assumed to be able to predict well ahead into the future. Do you think that's realistic? Right? Now, if you have played chess game, you know how difficult that is. Even top players can't predict that many steps ahead in time. There's so many variables to consider. Even when computers play chess games, they don't try to predict every single possible move. Even computers would use some heuristic rules because it's just too difficult to consider all possibilities. Yet game theory assumes that humans can do that. We assume that the players can effortlessly predict into the future for as long as they need. Right? And it could be very long because the game could be played repeatedly between players, right? So I know what you're going to do next. And you know what I'm going to do next. And I know what you know about what I'm going to do next. And then you know what I know about what I'm going to do next. It gets very complicated very soon. It's a constant joke among game theorists. You know, I know, you know, I know, you know, I know, you know, I know what you're going to do. So this is an assumption made that is highly contestable because if computers can't do it, it's highly unlikely that humans can do it. That's one. Complete plan. The requirement of subgame perfect equilibrium is you have to have a plan for every possible scenario. Do we do that in reality? Let me ask you, what's your plan if there's an earthquake in Hong Kong in the next 5 minutes? You probably don't have a plan, right? But the chance of Hong Kong having an earthquake in the next 5 minutes is not zero. There is a chance that Hong Kong is going to have an earthquake. The last time we had an earthquake is 60 years ago, something like that. So it has been a long time, but there is a chance that Hong Kong has an earthquake, will get an earthquake. Real humans do not have plans for every single possible scenario because there are just too many of them, right? So game theory assumes that's the case. Now this assumption is usually okay because we do not try to map out every single possibilities in a game, right? We usually, in a game, we have only the important decisions inside the game. Usually people do have plans for important decisions. So that might be okay. And finally, as we have mentioned, optimal plan. Players have planned to do what's optimal within each subgame, and I've already explained. Empty threats do occur
in reality, quite often, right? So it's when we only focus on subgame perfect equilibrium, it rules out some interesting behavior. So there are a few ways around that in a more advanced game theory course. One is you can relax the assumption of the equilibrium. Instead of requiring a perfect decision, you can allow for less than perfect strategies. Another possibility is you could have added in uncertainty, right? Part of the reason why empty threads work is that you're not certain that it is really empty. When the girlfriend threatens to jump, can the boyfriend be certain, 100% certain, that she's not going to do that? And sometimes they are overly certain because we do have people jumping out of buildings. So you know that this is not easy. When you have uncertainty, then you change. The game is different. It's It's more complicated to study. And if you're interested in that, take the 3000 level game theory course. Right, now it's your turn. So, suppose small potato is considered whether to enter the market currently dominated by Superman Lee. Superman Lee has to consider whether to fight back if small potato does, but fighting is costly. Find the Nash equilibrium in the normal form game and find the subgame perfect equilibrium in the extensive form game. So take a look, try to figure out what would happen in these two cases. Seems like the airport at this point. So noisy. Action 咧就係我做某做投資法定一樣啦。Strategy 咧係呢個策略，個策略係可以視乎你對方做乜咗，你會改變你。即係啊，所以你頭先個即係頭先佢睇個例子啊，喺動作片咧就。喺佢愛情片入邊你個但係你個策略不可以睇。佢睇愛情，佢睇動作片，佢睇愛情片，呢個就係個 策略啦，咁樣策略係可以，你可以係根據唔同情況嘅 action。嗱，最後咧，頭先我哋講過啦，最後出現嘅情況係，你係兩個都可以睇台嘅，係啊，佢冇最後佢睇動作片係冇睇。你呢度你個十邊需要香港要嗰陣咧，係要求你冇出現嗰啲情況咧，如果出現咧，嗰個呢人呢度揀一個係最一個最揀一個最好嘅時間。你唔可以話，如果個女仔去睇，如果個 Mary 佢去睇動作片，我去睇動作片，我就去睇愛情片啦。呢個唔係一個最好嘅時間。如果佢睇愛情動作片，你應該去睇個男仔呢個動作片。係啦，雖然呢個情況係發生嘅最後，因為個女仔係會揀去睇愛情，但係你都唔可以，即係出現嘅嘢點解唔可以？即係已出現嘅嘢，反正都唔出現啦，亂咁嚟都冇影響㗎啦。但係你好多嘢咧係包含係冇出現嘅情況。冇出現情況都一樣要有個計劃，個計劃都係要係最好嘅。因為頭先就講過啦，如果你容許佢咧喺冇出現嘅情況有啲唔合理嘅計劃咧，呢個唔合理嘅計劃可以影響成個呢個價錢。所以咪最後即係話你唔係啦，你係啦，分手又跳樓，咁你跟住又分手。有呢個係會令個 friend 係啦，冇錯。分手就跳樓，於是分手，咁你冇做啊，對唔對？咁你永遠都唔知佢之後跳樓。咁但係就影響咗嗰個好多年，因為佢話分手就跳樓，所以分手。係啦。咁就唔係佢嘅。如果佢分咗手都係佢跳樓，佢就唔可以喺呢度喺個十經飛過嗰陣咧，佢係唔可以話分手就跳樓嘅，因為佢真係佢嘅。
All right. So let's take a look. Let's start with what small potato would do. In the normal form game, suppose Superman Lee accommodates. Small potato staying out gets 0, coming in gets 2, so he's going to come in. If Superman Lee decides to fight, small potato staying out gets 0, coming in gets 3, so he's going to So small coming in get -3, so he's going to stay out. If small potato decides to stay out, Superman Lee can accommodate or fight. In this case, it actually doesn't matter. So he's willing to do either. And if small potato stays, if small potato comes in, Superman Lee can choose between accommodating and fighting is too costly, so he's actually going to accommodate. So you have two pure strategy, Nash, equilibrium in this case, equilibria in this case. The case of in accommodate and the case of out and fight. This is normal form. What about the extensive form? Remember, in the extensive form, you have to start solving from the back. So let's start this. There's only one subgame, meaningful subgame in this case. It's just this case. Superman Lee can choose between accommodating and fighting if small potato has already come in. And he's choosing between, I've copied the numbers where, okay, so it's the second number here. So Superman Lee is going to get 1 if he accommodates and fight if small potato already comes in, so he's going to accommodate. And then you go back to the bigger subgame. what would small potato do? If small potato stays out, he's going to get 0. If he comes in, he knows that Superman is going to come accommodate, he's going to get 2, so he's going to come in. So there's only one subgame perfect equilibrium in this case. That is Supermanly. In this case, actually, accommodate if small potato comes in. It could be anything. Doesn't really matter because they are the same. They give the same payoff. If small potato stays out, it doesn't actually affect it doesn't affect what happens. And small potato, not small photo, small potato in. Okay? So that's the subgame perfect equilibrium. Notice that in this case, there's once again a first mover advantage. Small potato moving first. Choose to force Superman Lee's hand and enter. What if you switch the order and Superman Lee move first? Right? If Superman Lee move first, you can actually try drawing out the game. Next, let's look at this one. Matching pennies. Alright, so the idea of the game is player 1 wins by so two players each put forward a side of the coin. Player 1 wins by matching the coin of player 2, and player 2 wins by mismatching. Alright? What's the Nash equilibrium in this case? Do you have any Nash equilibrium? If you think about it carefully for just a few seconds, right? It's hard. It's difficult for there to be an equilibrium in this case. I win by matching your coin, and you win by mismatching my coin. When I win, you lose, and when you win, I lose. So there's no. Our incentives are completely opposite of each other. So if I put heads, you want to put tails. If you put tails, I want to put tails too. If I put tails, you want to put head. And if you put head, I want to put head. So you have this cycle where you will never settle on a particular outcome. And we can show that. We can show that. Let's try. Suppose player 2 has already put forward a head, right? Let's say player 1 knows that player 2 is going to put forward a head. Maybe player 2 is like two-faced, so the coin is always heads and heads, right? That's why it's called two-faced. So if player 2 put forward a head, player 1 wants to. If player 1 puts forward a head, he gets -1. If you put a tail, he gets -1. Remember, he wins by matching, so he's going to choose heads. If player 2 put forward a tail, if player 2 chooses to put forward a tail, then player 1 gets 1 by matching, so he's going to match and put forward a tail. Player 2. Suppose player 1 chooses a head. What would player 2 do? He can choose between -1 by matching or 1 by mismatching. So clearly, player 2 is going to try to mismatch and by putting forward a tail. And finally, if player 1 chooses tail, player 2 is going to mismatch by put forward a head. So as you see, there's no single cell with circles around all its numbers. So there is no pure strategy Nash equilibrium. Ooh. So it's hard to go through 2 classes. None. Dominating strategy. As you see, basically you're looking for lines with no circles or lines with all circles, and in this case there are none. There are no lines with all circles, and there are no lines with no circles. Basically, that's what you're looking for. So there are none. What happens in this case? Well, pure strategy Nash equilibrium does not always exist, and it does not exist in many cases. Think about the matching penny game. The matching penny game is really a simplified version of rock, paper, and scissors. It is really just a simplified version of rock, paper, scissors, right? And in the rock, paper, and scissors, your incentive is always misaligned, right? If I put rock, you win by paper. And if you put paper, I win by scissors. If I put scissors, you win by rock, and if you put rock, I win by paper, right? So incentive misalignment happens in reality. In those cases, it's helpful to think about what you do in rock, paper, and scissors. You always use the same action in rock, paper, and scissors. You know, right? No one just do this, right? No one always play with rock, right? That would guarantee you lose. So in rock, paper, scissors, what do? You randomize what you use, right? Rock, scissors, paper, rock, scissors, paper, or something like that. You randomize. You try to randomize. So this concept carries through here. When players cannot choose a single action, they randomize among different actions. That's called a mixed strategy Nash equilibrium. Each player chooses a probability to randomize among different actions, given the probabilities the other players have chosen, each player has no incentive to change her probability. Notice that the wording is very similar. We have altered this concept of stability. Instead of defining stability as choosing a single action, we are now defining stability as choosing a single probability. Right? A single probability distribution. It's still stable. We are using the same probability distribution. Okay? So in rock, paper, and scissors, usually that means you're using rock, paper, and scissors equally. The question is, how do you figure out the probability? How do you figure out the probability? Okay. To do that, let's think about rock, paper, and scissors. What would you do if I always use rock? What do? Rock. Paper, right? You always use paper. Okay, that should be obvious. You win 100% of the time. Now let's get to more complicated situations. What if I use rock 80% of the time? What do? Do you use paper 80% of the time? That seems a net tempting conclusion, right? Almost there. What should you use? You should still use paper all the time. That guarantees you 80% chance of winning. What if you use paper 80% of the time? If you use paper 80% of the time, there's an 80% chance that within those 80% time that you use paper, there's an 80% chance you're going to see my rock. So that's only a 64% chance of winning. Right? You must be always using paper to win 80% of the time. If you only use paper 80% of the time, you only win 64% of the time. You don't win 80% of the time. What if I use rock 40% of the time, paper and scissors each 30% of the time? What should you do? You should always use paper because that guarantees you that you win 40% of the time. That's still better than luck, right? If you only use paper 30% of the time, you only win in 40 times. In those cases, you won't be winning as often. You can try to calculate out all possibilities. The lesson here is that it's actually not easy for people to randomize. I must be doing something All right. So, anyone figure out what the numbers are? What the numbers are in this case? So, our father thinks of two positive integers. Then he tells his economist son the product of the two integers, and his economist daughter the sum. He asks his son, "Do you know the two integers?" He replies, "No, I do not." He asks his daughter, "Do you know the two integers?" She replies, "No, I do not." He asks his son again, "Do you know the two integers?" He replies, "No, I do not." And he asks his daughter, "Do you know the two integers?" She replies, "No, I do not." Then he asks his son, "Do you know the two integers?" He replies, "Yes, I do." And the daughter also says, "Yes, I do." All right. Anyone figure out the numbers? Anyone? Volunteer? What numbers they are? 1 6. 1 6. Anyone found 1 6? I think it's 1 6. All right, let's see. So here's the logic. Let's start with the sum. The sum knows the product, right? So if the product is 1, what could the two numbers be? 1, 1. So that's the only possibility. So if the product is actually 1, you already know the answer, right? That's going to be 1 and 1. So that cannot be the case. And more generally, the product cannot be a prime number, right? Cannot be a prime number because a prime number, by definition, can only be the product of itself and 1, which would immediately let you know that those are two numbers, right? If I told you the product is 7, the only possibility is 7 and 1. Okay, so we can cross out all the prime numbers. Right, that means it's not 2, 1. It's not so I think the number in the back is the product, right? So it's not, the product cannot be 1, the product cannot be 2, the product cannot be 3, the product cannot be 5, nor 7, right? So we have to eliminate those. Okay. Next, now consider the sum. What are the possibilities for the sum? What are the possibilities for the sum of 4? How do you get a sum of 4? You can have 1 plus 3 or 2 plus 2, right? We have already notice that we have just eliminated the possibility of 3 and 1 because 3 times 1 is 3. So that couldn't be the case. Otherwise, the son would have already told you that he knows what the number is. The numbers are. So that means if the sum is actually 4, the daughter should have known by this point that it's the two numbers are 2 and 2, right? Because we have already eliminated 3 and 1. If the daughter says she doesn't know the number, then the two numbers, then the sum cannot be 4 because she would have known that it's 2 and 2. So we have to eliminate 4. So the first step, no primes. The second step, you eliminate the sum of 4. Okay? Sum cannot be 4 in the second step. Next. So you have to eliminate 2 and 2. The next step is, can the product be 4? How do you get a product of 4? You can have 4 times 1 or 2 times 2. So we have just eliminated 2 times 2. Right? We just eliminated 2 and 2, so it can't be 2 times 2. So if the product is actually 4, then the son should know by the third step that the two numbers are 1 and 4. But he says he doesn't know, which means the product is not 4. We can eliminate that. So this is number 2. Step 3. Step 4. Okay, actually, sorry. This is 3. this is 2. Now, then he asks his daughter again, do you know the 2 integers? Reply, no, I do not. So you should start to notice a pattern here, right? Basically, every time we look at what we have just eliminated, and that would allow us to eliminate another set of numbers in turn. So we have just eliminated 4 and 1, and 4 and 1 sum up to 5. How do you get a sum of 5? 1 plus 4 or 2 plus 3? But since we have just eliminated 1 plus 4, if it's really 2 plus 3, we would have known by now. But we do not know yet, so we can eliminate 2 and 3. Finally, he asks his son, do you know the 2 integers? And he says, yes. Well, we just eliminated 2 and 3. 2 and 3 multiplied to 6. We have, so there, what's possibilities there are? 2 times 3 equals 6, and 6 times 1 equals 6. For that reason, the correct answer would be 6 and 1, right? So that's how this game works. This game can last for a long time because basically you just keep extending the number of no, I do not, and you can keep pushing forward the numbers. So this is mathematical induction, which you have learned in high school. The key is, game theory says, you should be able to get this information from the dialogue, just like that, which clearly is very difficult, right? Once again, a lot of game theoretical and many game theoretical situations require quite a bit of thinking, even though the model kind of assumes that people can